Hello students, today we are going to see our next practical, which is exponential decay of amplitude of the simple pendulum. So you can see here AM apparatus. I will show you how to draw the diagram and formulae. Here there are some observations we have to take, and this is observation table will look like. We have to plot a graph and then calculation and result. So I will show you first how to draw the diagram in the journal. You have to do such pendulum, just simple pendulum, and here it will be the support, and then first you can draw like this. Now you can draw like this, show that the amplitude is decreasing. Do this with a dotted lines so that we can say that this is in as the time progresses the amplitude is decreasing. So you have to draw this diagram. Then these are some formulae. This lambda is called logarithmic decrement. We are not just noting the decrease in the amplitude, but also we are taking its log, and we will see how to do that. We have to measure the number of oscillations and we have to multiply it by 2 so that we get half oscillation. So what I mean here, one oscillation is from this to this and half oscillation is just from this to this. So we have to take number of oscillation and number of half oscillations, and we have to use this in this formula. Here A naught is the initial amplitude and an is the nth amplitude, or we can say amplitude after n half oscillations. L is the length of pendulum, which we are going to see in the simulation. Theta naught is initial angle, because in the simulation we are not measuring the amplitude directly. We will first measure the angle and then from that we will find out the amplitude. Then we will fill up this observation table. So let us go to the simulation. Here I will be sharing this link to you. Go to the intro. Now by default there is a ruler, but we cannot measure the amplitude in this horizontal direction. We cannot rotate this scale, so we will not need this. The length of pendulum is already given here. You can change this length as per your wish. You can change the mass, but we will keep this 1 kg. And if I start oscillating this pendulum, you will observe that the amplitude is not decaying because there is no friction. So first of all, what we will do, we will add some friction in this, so amplitude will decay. As the friction is going to be increased, the pendulum will be stopped immediately. So let's start with this friction, and I will start from 25 degree angle. Okay, so if I release this, you can see at this friction the amplitude is decaying with very slow rate. But suppose if I increase the friction, now you can see the amplitude is quickly decaying. Suppose I have lots of friction, then this pendulum will damp very quickly and the amplitude will become 0 very soon. So we will not use this lots and none. So we will use some friction in between this. You can choose that randomly and then you can perform the experiment. Here we don't have to measure the time period. What we have to measure is the amplitude. In this case we cannot directly measure the amplitude, so we will measure the angle, and you can see this is L and there will be angle theta here. So our amplitude will be L sin theta, because the side in front of the angle will be sin theta. So L sin theta is our amplitude. So you can calculate that and put it here. So first observation will be obviously at n equal to 0, that is initial case, and that time we will measure the theta. You can get 25 degree or 20 degrees And then after calculating or after noting all the amplitudes, you take the ratio with the initial amplitude and the final amplitudes, then take the logarithm that is base to the 10, and then you can take the ratio of this logarithm and divide it by the number of Hawk oscillation. You can do this and take the mean of all the observations, all the calculations, so that you can get the logarithmic decrement by the calculation. Now, to calculate logarithmic decrement by the graph, you have to plot the graph of log of this quantity to n. So, on the y-axis we will plot this quantity, this number, whatever the readings you will get here, and the half oscillation on the x-axis. So, I will quickly show. The graph will look like this. Here you will plot n, and here the log will be plotted along y-axis. Okay, so water quantity, I am not writing everything. So you will get almost a straight line, and you have to take the slope of this graph. By calculation we take the mean, and graphically we take the slope, and that will be our logarithmic decrement by graph. Okay, so I will now go to the simulation again. Now this can be done in two different ways. First, you can fix the n, that is fixed interval of half oscillation or full oscillation, and then note the angle. Or you can do another thing, you can fix the angles. Let's say I am releasing it from 30 degree, and then calculate the number of oscillation, say 3, 4, 5, to become this 25 degree, 20 degree. That will be easier. So you will fix theta here, and then accordingly you can find out the n here. Or you can do another way, you can fix n, that is 10, 20, or here 10, 20, and here it will be 20, 40, like this, so that you have to measure the angle. This will be difficult, so I will suggest you to fix angles first and then measure the n, that is half oscillation. First we will measure full oscillation. I will show you quickly one reading. Keep friction here, and length is fixed 0.7 meter or 70 centimeter. Now I will keep the angle fixed. Let's say I will keep, for just showing, I will keep 20 degree. You can see the initial angle, and then all the big lines show 5 degrees. So I will note first 20 degree, and then I will note 15 degree. So I will release this 1, 2. So for the second oscillation itself, the amplitude is decayed to 15 degrees because I have kept the friction very large. So if it is less, suppose it is at this position, then I will do the experiment again. You can see here at 20 degree, I have released this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So almost 10 or 11 oscillations we get to decrease this amplitude by 5 degree. This is angular amplitude. So you can take here 11, or let's say 10. Then here you will write 20. You have to just multiply this with 2. So here it is written wrong. Here it should be n equal to 2n. I will correct this, and I will share the corrected PDF to you. So it should be, first you will note the full oscillation, and then you will note the half oscillation, which is we are denoting by n, or here you can write n by 2. Okay, and then else next calculation is the same. So you will get some value for lambda from this observation table and also from the graph. So graph of the log and this n is nothing but the logarithmic decrement. You can open this from your mobile phones also. So click on the intro, then you can see all this parameter as we have shown in the as I have shown on the laptop. So change the friction. You need not to change the length or mass, you can just fix that, and then at some angle you can release, let's say 25 degree, and then measure number of periods to become it 20 degree, 15 degree, 10 degree, and so on. You can see below there are pause button, so I have clicked the pause button. So to measure the exact amplitude you can also use this, and if I click it again it will resume oscillating.